Okay, this is going to be a review of pretty much everything we've done with stoichiometry up to this point. So we will be looking at several different topics, and we're going to start with molar mass, because if you can't find the molar mass of a compound, then you can't do any of the rest of this. So, molar mass. Example I gave here is iron 3 oxide, or Fe2O3, and I'm going to use it through several of the examples so we don't have to keep calculating it over and over again. Okay, so the first thing you must do is look at your periodic table, which I drew the squares over here, and find the molar mass on the periodic table of the atoms that you are dealing with, or the elements that you're dealing with. So iron's molar mass is here. It is the 55.845 number. And oxygen's is also in the same location. So that might be on the bottom, in the middle. It could be in the upper right corner. It could be in the upper left corner. It all depends on what periodic table you're looking at. It could also vary slightly, maybe more accurate, so have more digits after the decimal, or less accurate and have less digits after the decimal, or maybe no decimal points at all if it's a very, very basic periodic table. But for this one, the one that I'm using, all the elements have 5 or 6 significant figures. So, calculating the molar mass, what we need to do is we will find iron on our periodic table, which I've got over here, and that has a molar mass of 55.845. Now, to calculate the molar mass of this compound, we need to multiply by how many atoms are in the compound. So 55.845 times 2 is 111.69. And then we have oxygen, which is 15.9994. And we have 3 of those. So we're going to multiply that by 3. And we get 47.9982. Then we will add those together, and we get not the number I just got on the calculator. $159.69. 0.6882. And then we are going to round. It works out to this decimal place because we're adding these digits together. So we're going to round to 159.69 grams per mole. So what that means is that every 1 mole equals 159.69 grams. Just like 5 200 shilling coins equals 1,000 shillings, or would be the same as a 1,000 shilling note. So to find molar mass, you multiply mass from periodic table by number of atoms in a molecule of whatever it is you're looking for. In this case, it was Fe2O3. And you do that for all of the atoms. Of the molecule. And add them together. Okay, so that's finding molar mass. Now, like I said, we are going to use the molar mass of iron oxide for the other things. So I'm going to take this number. I've actually already taken this number and copied it down on the next page. So this number here is the same number we just found, and we're going to use it for our moles to grams. Every time you have moles of something, any compound or element or atom, and you want to find out, or if you have grams of something and you want to find out how many moles, it's always going to be the same process. So in this question, we have 472.1 gram of iron 3 oxide. So we're going to take our 472.1 grams and multiply by what we want, 1 mole, what we want moles, and we're going to divide by what is equal to 1 mole, which is 159.69 grams, as we determined from finding the molar mass. Every 1 mole of iron 3 oxide weighs 159.69 grams. So 1 mole divided by 159.69 grams is literally changing the unit. It's like multiplying or dividing by 1, because they are equal to the same amount. So when we punch that into the calculator, 472.1 divided by 159.69, we get 2.9563. And we canceled out our grams, so we have moles of iron 3 oxide. Now, in our problem, they gave us 4 significant figures. We're using a periodic table that gives us 5 or 6 for every element that we're going to deal with. So we are going to round to 4 significant figures, which would be this spot. So that 3 is going to make that 6 remain a 6. So our final answer for this problem would be 2.956 moles of Fe2O3. So our step for converting from moles to grams is from moles from grams is to take grams of the substance and divide by the molar mass. So that's the step that you must take for this process. Okay, let's look at the next one. Moles from atoms. So in this one, you don't need the molar mass, so I didn't write it down over here. What you do need is Avogadro's number. 6.022 times 10 to the 23rd atoms, or molecules, or units, or little thingies. Avogadro's number is just, so it's 6.022 times 10 to the 23rd, and that means that a whole bunch of things that equals 1 mole. That's how many atoms are in 1 mole. So it's the exact same principle as how many grams are in 1 mole. This is just looking at atoms or molecules or units, whatever we're looking at. So we're going to say we have these iron 3 oxide molecules, and we have 5.87 times 10 to the 23rd of them. So we want to find out how many moles we have. So just like last time, we're going to multiply by what we want on top. And remember, we're essentially multiplying by 1. 1 mole is equal to 6.022 times 10 to the 23rd atoms, or molecules. I guess I wrote molecules there, so I'll write molecules again. And that will get rid of our molecules, and we will end up with moles. So 5.87 times 10 to the 23rd divided by 6.022 times 10 to the 23rd is going to give us 0.97475. So that equals 0.97475, and that's far enough for us to round. We have 3 significant figures in the question. We have 4 significant figures in Avogadro's number, so we are going to round to the 3rd significant figure. So this 4 will become a 5 because the 7 is larger than 5. So the final answer will be 0.975 moles of Fe2O3. So the main takeaway here is anytime you're going from atoms to moles, you want to take the number of atoms you have and divide by Avogadro's number. And again, atoms could be atoms, it could be molecules, it could be units. If you had a mole of puppies, or you wanted to find out how many moles of puppies you have, it could be puppies. It can be any item. Typically, they're really small items, like atoms. All right. Now, we want to find out how many atoms we have, and we know how many moles we have. So again, in this one, we just need Avogadro's number. And this is atoms per mole. So in this case, we're going to take the number of moles we have, which we're still using iron oxide as our example, and we are going to multiply by 6.022 times 10 to the 23rd. It's very important that you put this times 10 to the 23rd there. Atoms per 1 mole. And again, this should probably be molecules. So we're going to take 1.67 times 6.022 times 10 to the 23rd, and we get 1.00567 times 10 to the 24th atoms of Fe2O3, or molecules. So, once we have that, we need to decide how many significant figures we need. Again, our problem gave us 3, so we are going to round to this 0. Now, since this number here is a 5, we round to the even number, and 0 is considered even. So we are going to round to 1.00 times 10 to the 24th molecules. So our take-home step from this, anytime you are going from moles to atoms, you multiply by Avogadro's number. Number of moles times Avogadro's number. And that will get you there every time. Okay. Now let's look at going from moles to grams. Oh, I didn't copy down the molar mass of iron oxide on this one, so let's go back and find it. $159.69 grams per mole, because we calculated that earlier. So 159.69 grams per mole. There's our molar mass of iron oxide. So we know how many moles we have. We have 2.81 moles. So we're going to multiply by 159.69 grams for every 1 mole. And that will tell us our answer. 2.81 times 159.69 equals 448.728 grams of Fe2O3. Again, I use 3 significant figures here, so we need to round to the 3rd significant figure. So this 8 will become a 9 because the 7 is above 5. So our final answer here, 449 grams of Fe2O3. The takeaway from this one, number of moles and multiply by the molar mass. Okay, now what we need to do is make sure that we can remember how to balance chemical equations, because if we can't balance a chemical equation when we get into reaction stoichiometry, we are not going to be able to properly solve it. So I set up a chemical equation here. Of course, I didn't use iron oxide in it, so that means we're going to have to calculate more molar masses, but that's okay. So the way I like to do it, I like to write down what I have on each side. So I've got carbon, hydrogen, and oxygen on both sides. Got 7 carbon, 16 hydrogen, and 2 oxygen. And on the other side, I write them in the same order so I can compare them easily. I have 1 carbon, I have 2 hydrogen, and I have 2 plus 1 oxygens, or 3. Okay, so I'm gonna deal with oxygen last because I've got it in 2 spots over here. So if I change one, I might have to change another, and I'm gonna start with my carbon. So I'm gonna multiply carbon by 7, which means I need to put a 7 here. And that's also gonna change my oxygen that I have 2 of So this oxygen is going to get multiplied by 7. So now I have 14 plus 1, which becomes 15 oxygen on this side. Okay, next I'm going to move to hydrogen. I've got 16 on the left-hand side, and I've only got 2 on the right-hand side. I can easily multiply 2 by 8 to get 16 hydrogens. And that also changes my oxygen that I have 1 of times 8. So now I have 14 plus 8, or 22 oxygen. Now luckily, I can change this 2 into 22 by multiplying by 11. So now I have a balanced equation. I'm going to move on. I'm going to use the same equation when we do an example of reaction stoichiometry. Okay. So, again, I've got the periodic table boxes over on the right-hand side of the elements that we're going to be dealing with, and I've got the question written out. If 11.1 grams of O2 reacts completely according to this reaction that you're given, how many grams of water will be produced? So the first thing we need to do is get to moles of O2. So if we go back to see how to go from grams to moles, moles from grams. Take the grams and divide by the molar mass. So we need the molar mass so we can divide by it. So we are going to multiply by 1 mole over the molar mass of O2. Find the molar mass of O2. We need to take 15.9994 and multiply by 2. And that will tell us what our molar mass is, which is 31.9988 grams per mole. So 31.9988. So the first step, which will tell us how many moles of oxygen we have, is to take 11.1 and divide by that number, 31.9988, and we find that we have 0.34688 moles of O2. So that's step 1. Step 1, find the moles of what you're given. Sometimes you'll be given that in moles, and then you already have that answer. But in this case, we were given grams. Step 2 is to figure out, to use our molar ratio, which we have up here. We have our coefficients, and our balanced chemical equation is our molar ratio. Every 11 moles of O2 that is used produces 8 moles of water. So we're going to take the answer we got from step 1, and we want to find out how many moles of water that's going to equal. So we need to change from moles of O2 into moles of water. So we want our moles of water on top. Our conversion factor for moles of water is 8 moles of H2O for every 11 moles of what we want to get rid of, which is O2. So we're going to take our previous answer, we're going to multiply by 8, and then we're going to divide by 11. And that tells us that we have 0.252282 moles of H2O will be produced. And then step 3, we are going to find out how many grams of water. Now, if we know how many moles of water we have, so if we go back here and look, we know how many moles of water we have, and we need grams, so we need to follow this rule. So number of moles times the molar mass. So we are going to take our 0.252282, and I've got a bunch of other numbers still in my calculator. I don't ever clear it until I get to the end. Moles of H2O, and we are going to multiply that by the molar mass of H2O. So we need to calculate the molar mass of H2O, which H is equal to 1.00784. We have 2 of those, and O is equal to 15.9994. We have 1 of those. We add those together, and we get 18.015 grams per mole. So we are going to multiply by 18.015 grams over 1 mole. That gets rid of our moles. We're not changing our compound, so we still have water. And we find that in that above reaction, 4.5448 grams of H2O is produced. So we had 3 significant figures at the beginning, so we need to have 3 significant figures at the end. So the final answer will be 4.54 grams of H2O. So our steps here. Step 1 was grams to moles. So divide by molar mass. Step 2 was use your molar ratio from balanced equation, which is this 8 and 11. And step 3 was multiply by the molar mass of the new substance. Obviously, if you were given atoms or asked for atoms, you would change and you would do the steps that we talked about back here. If you were looking for atoms at the end, after you found your moles and you did your molar conversion, you'd multiply by Avogadro's number. If you had atoms at the beginning, you would divide by Avogadro's number to get the moles of the original substance. But you can put these calculations together when dealing with reactions to find out about any of the things in the reaction. We could have said, if 11.1 grams of this reacts, how much of this reacts? And we can do that. We could use that 11-to-1 ratio the same way. Or we could have found carbon dioxide, but I chose oxygen, gas, and water for this example. Just make sure that you do those steps. And it's also important to remember that you can't go from from grams of O2 directly to anything else. You've got these numbers are a molar ratio. You have to have moles first. So you need to go grams of O2 to moles of O2, or atoms of O2 to moles of O2. And then you turn it into the moles of whatever it is you're looking for, and then you solve by doing the proper step to find either grams or atoms or molecules.